Today we're going to teach you guys about metamorphic rocks. First we'll start off with an introduction and then we'll go into foliated versus non-foliated rocks. After that we'll give you different examples of the textures of these and then we'll show you demonstrations of how the different metamorphic rocks are formed. After that we'll go into rock identification and then we'll play a game to see what you guys have learned.
The word metamorphic is derived from Greek and means of changed form. Metamorphic rocks are rocks changed from one form to another by intense heat, pressure, or the action of watery fluids. Inside Earth, all of these metamorphic processes are more intense and capable of changing rock from one form to another. Therefore, every metamorphic rock has a parent rock, also known as the protolith. The parent rock is the rock type that was transformed. Parent rocks can be any of the three main rock types, such as igneous rock, sedimentary rock, or even metamorphic rock. Metamorphic rocks can be formed by deep pressure under the Earth's surface, from the extreme heat caused by magma, or by the intense collisions and friction of tectonic plates. There are two main metamorphic processes: contact metamorphism and regional metamorphism. Contact metamorphism occurs locally and adjacent to igneous intrusions and along fractures that are in contact with hydrothermal fluids. It is caused by conditions of low to moderate pressure, intense heating, and reaction with hydrothermal fluids. Regional metamorphism occurs over very large areas and is generally accompanied by folding of rock layers. This type of metamorphism is caused by large igneous intrusions that form and cool over long periods of time. Metamorphic alteration of rock causes the texture and/or mineral composition to change. Most of Earth's crust is made up of metamorphic rocks, and you can find these unique rocks all over the world in many different shapes, sizes, and colors.
Foliated metamorphic rocks are formed within the Earth's interior under extremely high pressures that are unequal, occurring when the pressure is greater in one direction than it is in the others. This causes the minerals in the original rock to reorient themselves with the long and flat minerals aligning perpendicular to the greatest pressure direction. This reduces the overall pressure on the rocks and gives it the striped look. Foliated metamorphic rocks are identified based on texture. Here are some examples of foliated rocks. The first example of foliated metamorphic rocks is slate. Slate is formed at very low temperatures and pressures. Rock breaks along nearly perfectly parallel to the planes. This slate is then used in pool tables and as roofing materials. The next example is phylitic texture. Phyllite falls under this category. Phyllite forms in low to intermediate temperatures and pressures. It is slightly more crystallized, which gives the rock a shiny appearance. Layers may also be wavy and crinkled.
Next is schistose texture. A schist is an example of this, which is created under intermediate to high temperatures and pressures. These crystals are larger with the grains aligned in parallel to subparallel layers. Next is gneiss texture. An example of this is gneiss, which is formed under very high temperatures and pressures. It is coarse grain texture of alternating light and dark mineral bands. Non-foliated metamorphic rocks are formed around igneous intrusions, where the temperatures are high but the pressures are relatively low and equal in all directions. The original minerals within the rock recrystallize into larger sizes and the atoms become more tightly packed together, increasing the density of the rock. Non-foliated metamorphic rocks are identified on the basis of their composition.
Marble is the first example of non-foliated metamorphic rocks. Marble is composed of the mineral calcite is metamorphosized limestone. The next example of non-foliated metamorphic rocks is quartzite. Quartzite is composed of the mineral quartz and is metamorphosized sandstone.
Index minerals in metamorphic rocks indicate how much the original rock was metamorphosed. This is called the grade of metamorphism. With increasing temperature and pressure, the metamorphic grade also increases. The higher the metamorphic grade, the more the change the rock will be from its original form. Shown here are the rocks we previously talked about in order of increasing metamorphic grade.
For the first demonstration, I'll be showing you all how a sedimentary rock turns into a metamorphic rock. So the green, the yellow, and the red represent the different sediments that are layered on top of each other during weathering and the creation of a sedimentary rock. After undergoing heat and pressure, it then turns into a different rock, and that is through the rock cycle and how metamorphism works. Through pressure, the rock can then turn into a different type of rock. For example, granite and gneiss. Here you can see the foliation, and after much more compaction and heat, it can turn into even thinner lines and become even more finely compacted. The example of the melting crayons is an example of contact metamorphism. It occurs when magma intrudes or forces its way into existing rock. The heat of the magma bakes the surrounding rocks, causing them to change, such as the tips of the crayons, and creating them together. This is a local event, and the changes due to contact metamorphism are relatively small and are said to be low-grade metamorphism. And another example of contact metamorphism is the metamorphic rock marble. Marble is created from limestone that has been subjected to heat.
In addition to heat and pressure, fluid and strain are two other agents that cause metamorphism. And so this demonstration is going to show how strain factors in the creation of metamorphic rocks. And so strain is any change in the shape of the rock due to stress. And so this was going to grind and crush the mineral grains inside the rock. And so this strain, coupled with the heat and pressure, they are going to orient the rocks in layers. And so that's how one of the ways metamorphic rocks change is through the replacement or rearrangement of the molecules in the individual mineral grains. And so this demonstration is going to provide a visual of those layers going into place. So for this demonstration, each different type of chocolate we have here is going to be like a visualization of the different types of grains inside each of the rocks that will eventually be metamorphosed.
So as you can see, the chocolate has been put into layers with the white chocolate on the bottom, the regular chocolate in the middle, and then the M&Ms at the top. And so these different pieces would typically represent different types of sedimentary, igneous, or metamorphic rocks that have already been deposited in their respective layers.
So applying heat to metamorphic rocks allows them to more easily orient in layers. So we're going to add some heat.
So once the rocks are heated, pressure is also going to be added to increase the strain and change the chemical composition of the rock grains. So we're just going to add some pressure.
So this newly formed rock mass is now combined together, and this is a result of the change in the shape of the rock created by the increased strain that we put on it. And so this is going to simulate the metamorphism that occurs, which changes the chemical structure and realigns the rock grains into certain patterns and shapes. So as you see the layers created here. So I've just taken a cross section of the metamorphic rock that we have formed. And so as this demonstration shows, strain is a major component in the creation of layers in metamorphic rock, which you can see. Get a better view here of the white chocolate, regular chocolate, and M&Ms and how they've like formed into layers and combined together. And so the presence of mineral layers, this is also called foliation, is an extremely important factor in identifying and classifying metamorphic rock.
And so as the strain increases, this foliation, this layering is going to become more intense, meaning the minerals will sort themselves in the thicker layers.
In addition to heat, pressure, and strain, fluids are also an important component in metamorphism. A small amount of water and other fluids are present in almost all rocks, and since this water allows minerals to move more easily, the presence of fluid makes metamorphism easier. Without fluid present, it is harder for chemical changes to occur. In this tutorial, I'm going to demonstrate how fluids can help change a rock, additionally showing how some metamorphic rocks change in composition and become foliated. First, we're going to take a regular paper towel and apply pressure to it, causing it to fold upward in one direction. This represents a geological uplift event. Now I'm going to spray the paper towel with water, representing the change that the rock undergoes when fluids are present. After spraying the water on, I'm going to apply the same amount of pressure and push inward. Now the paper towel has more folds that represent how a metamorphic rock that contains folds after it goes through compositional or chemical changes. Many open spaces between the grains and sedimentary rocks and the small fractures in igneous rocks are called pores. These pores are filled with fluid, and this fluid typically has dissolved ions in it. When temperature and pressure change during metamorphism, this also changes the composition of the fluid. The fluid then moves dissolved ions in and out of the minerals, starting a transportation that speeds up the chemical reactions that are taking place. Additionally, fluids are useful in the metamorphic process, and that the more fluids there are, the easier it is for the rock to melt. Since fluids allow chemicals to move more quickly, the increased mobility makes melting easier.